Sodium chloride is one of the most common compounds that we find, and or more commonly, table salt. It is from a sodium atom and a chlorine atom. The sodium atom, it has one valence electron, and the chlorine atom has seven. Clearly, if the sodium atom is just one valence electron from becoming stable and fulfilling the octet rule, and the chlorine atom is needs just one more electron to become uh, stable. So this brings us to an interesting problem. There's no way we could do a covalent bond such that you can fulfill the octet rule for both. However, there is one thing we can do: transfer the electron. We can take this electron and we can literally just put it over here. So we have sodium here with no valence electrons, or it's more properly stated to have it having all 8 in this case. And then chlorine is also completely stable with all 8. And there's one other side effect of this. This chlorine atom has one more electron than it's supposed to have, so it has a -1 charge denoted by the -1, and the sodium atom is missing one electron, so it has a +1 charge. And now what we have here is that we have the sodium atom with a +1 and the chlorine atom with a -1. And when we draw this, we draw the two slightly closer than we would in a covalent bond because the +1 force attracts the -1 force. And this is the definition of ionic bond, where the ionic bond is where you have electrons transferred and the octet rule is fulfilled, and to fulfill the octet rule, and bonded together because of the attraction between the two positive and negative ions that are formed, hence the word ionic. Metallic bonds are the type of bonds used by metals, hence why they're called metallic bonds. They're different from the other bonds we've seen because, unlike having a single set of atoms forming a single molecule, they come in large numbers. What you end up having is a bunch of protons and then just within all of the empty spaces between the protons, just electrons constantly bouncing from proton to proton. And this arrangement basically ends up to make it hard to draw a fine distinction on where an individual molecule is, and it cannot be represented with a Lewis diagram. So what we think about here is that this is it's the electron field basically, and within it this provides a lot of interesting properties. For instance, conductivity, specifically of electricity and heat. Electricity is when we have electrons flowing through the material, and when you have so much empty space and so little bonds, but only bonded as an entire compound, it's fairly trivial just to take an electron and just have it go through the path of the metal because it just blends in. It unbonds as seamlessly as it bonds. As well, we can do the same thing as heat, because heat is when the electrons are moving faster, so instead of going slowly, they're going quickly, and the reason we can do this is because when you have so many atoms that aren't really bonded to so many electrons not bonded to any specific atom, it's easy to have them go a completely different speed than normal. So that also helps. They have really high melting points, however, because there are while they're not attached on a molecule, very attached on a molecule by molecule basis, as an entire compound, as this whole entire thing, there is a very strong attachment, and it takes a lot of energy to break apart every single molecule into a separate part. And so so that gives to their high melting and boiling points. And those are the main properties of metallic bonds, and it's and these bonds form in metals, which are generally going to be the everything that occupies the d block. Another type of bond is the polar bond. Polar bonds by themselves aren't actually their own type of bond. In their rawest form, they're actually called polar covalent bonds. And in the exercise for covalent bonds, I had to draw a Lewis diagram for water, H2O. However, water is a polar bond, and and here's why. A polar bond is formed from very lopsided atoms in a bond. And as you probably know, everything has gravity, and atoms are no exception. And gravity is directly proportional to size. So if we have a big oxygen molecule, this will have with 8 protons. This will have and we have an equivalent hydrogen molecule with 1 proton. This is a drastic oversimplification, but in effect, the hydrogen molecule will have 1/8 the gravity of the oxygen. And so this may not seem like an important fact. However, now consider that this oxygen is now pulling the hydrogen into it. And what you end up having is that these hydrogen molecules are it's causing the entire molecule to be really lopsided, and you end up having something that looks like this, where this is the oxygen, giant O, and then just tiny little H's. One of the reasons it's interesting is now consider when we have another hydrogen water molecule with us. So if we have the one water here and another water here, what you end up the polar bonds are constantly breaking and rearranging themselves, so this hydrogen atom will actually go to this oxygen, which destabilizes this, and now this hydrogen might be forced to go here, which this one doesn't like, so it goes here, etc., etc. And it causes this really unstable arrangement, and you see polar bonds in big numbers. And this is the reason why when you have a glass of water, it can travel up and down really easily despite gravity, and it's able to stick to other polar molecules or other bits of water extremely easily. And polar bonds are cool, but yeah, and they have some interesting properties. And to say the least, if water was not polar, I would not be making this video right now. So yeah, don't forget your polar bonds. In order to understand why atoms bond, we first have to look at the octet rule. The octet rule states that within an atom, it is most stable if all of its valence electron slots are filled. There are usually 8 valence electron slots, except in a few more complex cases, and therefore it's called the octet rule, where oct means 8. So first of all, valence electrons. If we use the primitive model of having an atom as just having little rings of electrons around it, you have a bunch of different rings at different energy levels. That is, they have different amounts of energy in the electrons, and therefore different distance from the nucleus. The valence electrons are the electrons in the outermost energy level. So in this case, this here is the valence electrons. So, what this means is that if we had an electron here, an electron here, an electron here, this atom, whatever it might be, it has 3 valence electrons. So, the octet rule would state that this atom would only become stable if it can somehow gain 5 more electrons or lose 3 electrons. So, the next thing that we have to deal with here is how would we get this? How would we suddenly stabilize the elements? And this is why the octet rule is interesting in chemical bonding. If we start with the Lewis diagram, say the Lewis diagram for carbon, which looks like this because it has 4 valence electrons, what we basically have is a symbol in the middle and a dot for each valence electron. So this has 4 valence, and obviously it now needs a lot more in order to stabilize itself. So what we can do is have another carbon here, and what we basically end up doing is that we can draw a line between the two of them to stabilize each one, and now this. So what basically happens is that this electron is part of this one, and this electron is part of that one and that one. I'm gonna remove, and I'm gonna redo this a bit just so it's clear when we actually get to the Lewis diagram. So basically, you get the effect of having one more valence electron on each side. And as it turns out, it's kind of difficult to properly do a carbon diagram, but it's just easier to draw. However, to show properly Lewis diagrams, let's use oxygen. So oxygen has 6 valence, which I'm going to tell you right now is easier to work with. And so oxygen has 6 valence. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 6 and 6. So we need to get them both to 8. So if we say bond these two together, this becomes the effect of 7, and this also becomes the effect of 7. If we bond these two together, this becomes the effect of 8, and this also becomes the effect of 8. And so this is the Lewis diagram for an O2 molecule, which is just the everyday oxygen that we breathe in. So now the thing that we have to note is that this is only one of a few types of bond. This is the covalent bond. In a covalent bond, the octet rule is fulfilled by sharing electrons, which is why we draw the lines between them. And this way of looking at the atoms, which only works for covalent and ionic bonds, is called the Lewis diagram, which is where you have, which is where you use dots and lines to represent electrons and bonded electrons, respectively.